So welcome everyone to our STAMPS webinar series. It's a pleasure to introduce Dr. Michael Kagan. And if you go on to a conference with both the words machine learning and physics in the description, then there's a high chance that you've seen Michael before. So Michael Kagan is a lead staff scientist at SLAC National Accelerator Lab. He received his PhD in physics from Harvard University, and he did his postdoc work, and he was also a Panofsky Fellow at SLAC National Lab. So Michael's work focuses on the study of the Higgs boson and search for new physics at the ATLAS experiment at the Large Hadron Collider. And he's also working on the development on machine learning and AI for fundamental physics. And today he would, we asked him, so he would talk about using gradients to get more out of high energy physics. So Michael, please take it from here.
Yeah, thank you very much for inviting me and having me here. And thank you for the kind introduction. So yeah, I'm happy to tell you a little bit about some of the work we've been doing on basically thinking about how we can optimize sort of the kinds of data analysis systems we're working with in high energy physics, and specifically doing that with gradients. And so there's a lot of challenges in how we actually estimate those gradients. And so I'll try to take us through talking a little bit about a little bit of background in high energy physics, and then talk a little bit about some of the kinds of problems we want to solve and how we do that. So to kind of get us started, so I work in high energy physics. So sort of this slide sort of summarizes what we know. Effectively, what we care about is understanding the sort of fundamental constituents, the fundamental particles in the universe and how they interact with each other through particles that carry their forces. And so this ring is sort of the list of particles we know about, sort of the quarks on the top and what are called the leptons on the bottom. One of the leptons is an electron. And these basically make up the matter we know about in the universe. This blue ring are the particles that carry forces, like the photon, that carries that sort of transmits the electromagnetic force. And in the center is this bizarre particle called the Higgs boson that I study quite a bit. We're not really going to talk about that today, but it's the particle that sort of gives mass to all the other particles through its interactions. And so importantly, we have a theory for this known as the standard model. This is sort of the long form version of it. But given that this accounts for almost all the interactions of this matter that we know about, it's not so long. And it basically allows us to make computations of how these different particles interact and scatter off of each other. So we know quite a lot about how these particles interact. There's also a lot of stuff in terms of fundamental physics that we don't know. We don't really know why the Higgs boson has the properties that it does. Why is it so light? How does it interact with itself? Or potentially interact with new particles? It's a relatively newly discovered particle at CERN. We also don't really know what dark matter and dark energy are, even though we have lots of signs from sort of observational cosmology and astrophysics to know that it exists. And then there are sort of these grand questions, like why is there more matter than antimatter in the universe? Why didn't all of it annihilate in the beginning of the universe and leaving us with basically just light streaming out? So this question of why there's more matter than antimatter, we still also don't have an answer to. And the idea in collider physics is what we want to do is try to produce or find the particles that might be responsible for these kinds of behaviors and study those particles. And so we do that at the Large Hadron Collider at CERN right now. This is the highest energy collider in the world right now. It smashes together particles at 14 tera electron volts. And basically by smashing together particles with a lot of energy, we sort of know this equation, E equals mc squared. We can convert that energy of collision into, for instance, massive particles that might have been hanging around during the early universe, causing it to sort of evolve in a very specific way. So this collider is 27 kilometers around. It's 100 meters underground, and it has 4 major experiments on it. I work at Atlas. This is sort of the cartoon version of Atlas on the right. It's 25 meters tall and about 45 meters long. You can see you might be able to squint and see there's 2 people. They're sort of superimposed on the detector to see the relative size. And this detector is sort of built of layers of different kinds of detectors, sub-detectors, if you will. It's sort of like an onion where each of these layers helps you identify different kinds of particles. And so just to give you an idea of a little bit of what our data looks like, here you have a sort of beam pipe as this sort of white or gray bar going through the middle, and the particles come in from either side and smash together at the middle here. And then you see these yellow lines coming out. Those are charged particles flying out. And then they smash into detectors that will stop them and measure their energy. And that's what these sort of histograms are. These sort of yellow and green histograms are. And so you can see it's a sort of very heterogeneous, bespoke device designed really for the detection of high energy particles. And so in order to analyze this data, we have to sort of take detector signals coming out from this detector, and it's sort of accumulating data at 40 megahertz, 40 million times a second we're colliding. And this detector has 100 million detection elements. And we have to turn that into signatures of particles. So in each collision, we have to figure out what's the sort of particle content. And basically for each kind of particle we want to study, we develop algorithms for taking the data and estimating its properties, like its energy and its direction of travel, or its positions in the detector. And so there's sort of a cartoon on the right of sort of how you might do that for one kind of particle. So for instance, a particle might get produced in this collision point, what I put here in the blue, and it flies out, and it first leaves energy in what would look, or basically like digital cameras, pieces of silicon with very small pixels. They leave deposits of energy that we can sort of connect the dots and estimate the trajectory with, often using something like a Kalman filter. And then this particle smashes into what's called a calorimeter, which stops the particle and measures its energy. And we can sort of combine all this information and then use that to estimate the energy of this particle and classify what kind of particle it is. And so you can see on the left, this is a cross-sectional view of Atlas. The beams are coming into and out of the page and colliding at the middle. And you can see these charged particle trajectories here in purple, and then particles that smash into these red and green rings, which are calorimeters, and the histograms show how much energy was deposited. And you can see once we've run these algorithms, we can sort of identify what different kinds of particles are there. So in order to make all this work, we have to have a pretty good understanding of our data and the way that, and so you might ask the question, well, how can we do this? How can we understand the data and develop these algorithms? And the sort of key insight, or a very key and central part of this data analysis, is the fact that we have very, very precise simulations. So we have a very deep knowledge of this data generation process, starting from the standard model, this long equation, which has about 23 parameters. You can add more if you want to hypothesize or new particles. Then from this, we can sort of we can write down or calculate the probability of a given kind of interaction. In this case, the two protons interacting and producing like a Higgs boson and two top quarks, and they sort of immediately decay. So you can compute the sort of the distribution of these particles that come out of this hard collision. But those particles aren't really stable. They evolve, and they evolve until they sort of form pairs that are stable in the lifetime of the detector. So there's this evolution process that we can simulate. And then for each of those particles, around 100 of them per collision, they'll smash into the 100 million detector elements and produce signals. So you might sort of think, well, if we want to understand what's going on in the parameters of the theory, and we have 100 million pieces of information for every collision that has a very stochastic simulation process, there's a huge number of sort of latent pieces of information. And if we wanted to compute a likelihood, we'd have to integrate over all that information, which is basically impossible. It's intractable. So we don't try to do that. We don't try to estimate the likelihoods directly, but we can sort of simulate this chain, sort of like many of the processes here are essentially like Markov chains. And we can sample this process from sort of the beginning set of parameters and generate large numbers of simulated events. And then the process of analyzing the data, the way we can figure out how to do this sort of estimation, basically does this in reverse. Given these detector elements, we develop algorithms to reconstruct and identify each of those particles and estimate their properties. We then sort of look across all of our billions of events. We would look for events with the same sort of particle content, like looking for events that have 4 electrons in them. And then from that subset of events, we can run statistical inference. And so to sort of give you that picture here, the data analysis workflow basically starts, we have our experimental data and our simulated data, and we'll run them both through this sort of data analysis chain. And then what we can do is compare the simulation and data. And now we can't do that in sort of 100 million dimensions, but if we sort of reduce this into one very informative number, we can very easily do sort of comparing data and simulation using histograms. This is up until I'd say a lot of the machine learning revolutions, this has been our main tool, which is finding a very good variable that might separate signal and background. In this case, a Higgs boson here in blue versus the backgrounds in red. And by using this histogram to basically estimate densities, we can compare the data here in black with the simulation in blue and red. From there, with those densities, we can compute likelihood ratios and do things like frequentist interval estimation and hypothesis testing. So that's sort of the chain. And there's a lot of work in machine learning sort of within this data analysis chain to identify the different particles. There's work in simulation-based inference to move us away from one variable-based inference to sort of high-dimensional inference. And there's a lot of parameters going into this process. Parameters about, how we're going to, details of how we're going to run the simulation, or for instance, the parameters that define a detector in that simulation. We've got parameters in the data analysis, like what are the weights of all the machine learning models, or which different settings are you going to use for different algorithms. And so there's some level of tuning that you could do to try to optimize this system. Okay, we'll come back to that. But just to say, this process of sort of comparing data to simulation works very well. So here is, I love this plot, although I've been told by theoretical physicists that it's nearly useless. But for any sort of detailed comparisons between theory and data. But I think at the high level, what this shows is that on the x-axis is a series of different processes that you could study at the LHC. On the y-axis is effectively the rate at which they're produced. And this is a comparison in each of the colors is a measurement, and the gray bars are the theoretical predictions for how often each of these processes occur. And you can sort of see that that our theory and our experiment agree within about 14 orders of magnitude. So it's a very predictive theory. But moving forward, we're collecting more data. We're going to move to sort of higher intensity collisions at the LHC soon. We're going to be computing vast amounts of data. And we're even thinking about what the next collider and what the next detectors are going to look like. And so we want to get the most out of our current data, and, sort of improve our confidence intervals, reduce them as best we can. And we want to, for instance, maybe be thinking about how can we design systems that are going to give us the best sort of ability to do inference in the future. And so in some sense, these are questions about how do we optimize our data analysis and our detector design. And those are sort of a few of the kinds of questions that we might want to ask in optimizing our sort of data analysis systems. So you could sort of imagine, given the result, or some sort of predictive result, how can we optimize the data analysis to make the confidence intervals better? How can we tune a simulator to make them better match the observed data? How could we design new detectors to better optimize our inference capabilities in the future? Or how could you even do sort of like optimization-based inference if you wanted to? And that sort of is something that comes up a lot in like sort of analysis by inference schemes or sort of 3D reconstruction in medical imaging. We're not going to talk about optimization or inference through optimization, but we will talk a little bit about detector design and a little bit of some of the challenges that come up in building up an analysis optimization system, where we've sort of got a mix of different kinds of algorithms, physics-inspired numerical algorithms and machine learning algorithms, all in this mix of this data analysis pipeline. So maybe at a very high level, we can ask, what is it we're actually optimizing? And this is my equation for what we're optimizing here. We have some we have some basically distribution that we're sampling, for instance, from the simulation. It may have some parameters. We're from that distribution of possible events, we're going to, for instance, run our data analysis and evaluate some criteria like our confidence intervals or a detector design fidelity. How good was the detector? And we want to sort of get the average value of that objective across all the possible values of experimental data we may see. And the optimization would be sort of minimizing this process over the parameters of our system. So sort of breaking that down, we have this probability to see a measurement, and that sort of includes like the scattering and physics probabilities and the physics interaction probabilities and the detection probability. We have our sort of analysis and design parameters that this objective here in F depends on. And we have these realizations of the measurements we're going to be sort of integrating over. And since we can't actually do these integrations, what we're actually doing is Monte Carlo sampling, developing a Monte Carlo to sample this distribution, basically running the simulator and evaluating this function and seeing how well we do. And I sort of wrote it in this way because it looks a lot now like machine learning. And in fact, it looks a lot like you would think about a deep learning system. And in fact, that's sort of exactly what I want to get to, which is this idea that effectively we're sort of optimizing these Monte Carlo estimates of some objective, which is very similar to what you do in deep learning. And sort of the main optimization method of choice these days for optimizing neural networks, even up to sort of hundreds of billions of parameters, is gradient descent. It has a few more bells and whistles these days, but to sort of first order, you take the parameters, you compute the gradient of your loss or your objective, and you sort of update those parameters. And that allows you to sort of move your way through a loss landscape. Here might be the loss function as a function of the parameters, and move your way down to some minimum. And so that's going to be our goal. How can we sort of optimize our data analysis or simulation systems using things like gradient descent? And so the language this is often discussed in, or the way the sort of the high level is often talked about, is in the form of what's called differentiable programming. So differentiable programming is sort of a way to supercharge your code. So if your program is sort of some numerical program that takes in some data X and some parameters phi, and a normal program would sort of evaluate some function of X that depends on these parameters. Once you, in a differentiable programming same framework, you're basically developing what's called differentiable code via a technique called automatic differentiation. And effectively, this supercharging means that instead of the program just outputting the function, it's also going to output the function, the gradient of that function evaluated at the point X. And so this is basically the core essential ingredient to all the main machine learning frameworks that you may have worked with, TensorFlow, PyTorch, JAX, and others. Their main, most important aspect is the fact that they can do this computations of gradients and this via automatic differentiation. So I'm not going to do a deep dive into automatic differentiation today, but I will give you sort of a rough idea. So what the first step you do is once you've defined your program, once you define a function, what these automatic differentiation frameworks are going to do is they take that program as you write it and they break it down into a series of sort of atomic operations and the graph which specifies how you apply those operations. So here's a function with sort of two inputs, x1 and x2, and it computes this function f of x1 and x2. And here, the first thing that happens is the x1 gets passed through a sine function and also is multiplied by x2. Here's the multiplication function. And then they're added together. And that's the sort of computational graph of the system. And now at each of these points, you can define what the gradient would be from each of its inputs. And because you can define the gradient, you can sort of define, in high dimensions it would be the Jacobian, you can define the Jacobian at each of these steps and multiply them together via the chain rule. And now we're not going to symbolically derive, this doesn't symbolically derive the derivative, but it keeps into account what the appropriate derivative should be at each point in this chain and allows you to multiply them together. Importantly, either from the input to the output, or actually in reverse, in what's called reverse mode automatic differentiation, which is from the output back to the input. That would basically say, if I wiggle the output, how would that wiggle the inputs? Okay, so that's basically the computational tool behind automatic differentiation. And when you sort of start, when you think about this, although we use this a lot for machine learning, especially where these parameters are parameters of a neural network, anything can go in these programs, any sort of numerical code. We begin to sort of mix these sort of learnable machine learning components with sort of our domain-specific physics code. We might have a machine learning algorithm to classify some data we think is electrons, and a completely different piece of code that we use to identify a different kind of particle. And we want to be able to sort of jointly optimize these systems all together to optimize how well we can do any given sort of data analysis task. And so our goal then is, if we want to be able to jointly optimize these systems, optimize electrons while we're also taking into account optimizing other particles like muons, or anything else that helps us ultimately improve our confidence intervals, we need to be able to compute the derivatives of these sort of green blocks here, which would be our sort of physics code. And so this idea of building differentiable physics code is one that's sort of been gaining popularity, and this what we sort of call differentiable programming in HAP. And so there's a lot of examples of this, sort of piece by piece, making pieces of our simulation code or data analysis code differentiable so that we can consider these sort of jointly optimized systems. So we have some, for instance, differentiable simulators of how particles scatter off of each other, differentiable accelerator simulations, differentiable neutrino detectors, even sort of differentiable frequentist inference codes, and even the ability to sort of use a neural network to do sort of signal and background discrimination and optimize that through a sort of profile likelihood estimation. So there's a lot of examples of this kind of moving code into this differentiable format so that we can use it in concert with machine learning tools. So I'll give one example of some of the work we've did in this arena, and it's called jet classification. So jets are a specific kind of particle, it's a subset, Jets are a collimated stream of particles, as you can see in the bottom left. There's sort of a stream of particles coming from the collision at the bottom that flies out and smashes into this calorimeter, leaving the energy deposits in this histogram. You can sort of see different jets on the top left. This is a cross-sectional view of Atlas, and you can see each of these colored sprays of particles is a different jet. And they're produced from sort of high-energy quarks and gluons, and sometimes even by heavy particles like Higgs bosons that decay into these quarks. And so a very important task is to be able to separate, given a jet, what kind of particle produced it. And so as far as we're going to be considered now, just a jet is an unordered set of particles. And when I say particle, what I mean here is it's a list of sort of continuous valued features like momentum, direction, position. And we're going to take this list of features and we're going to try to classify these jets. And these days, in the sort of very machine learning very machine learning focused approaches, you'd basically just put this list of particles into a transformer or a graph neural network and try to train it for classification. But you basically just put this list of momentum, direction, and position. But what you sort of miss out on the fact is that these particles actually fly through the detector. We sort of summarize them with a given, one estimation of the momentum, but they're actually sort of trajectories that fly through, and that's sort of defined by the equations of motion. And the sort of geometry of what's going on inside of one of these jets can be very, very important. So classically, before machine learning was sort of the way that we did a lot of this jet tagging, one of the things we would do in order to find long-lived particles like bottom quarks would be look for vertices, basically track these trajectories, these equations of motion, and look for points where they cross somewhere away from the collision point on the far left. And sort of mathematically, the way you do that is each of these equations of motion, a particle moving in a magnetic field would be like a helix if it was a perfect magnetic field. And you would basically look for crossing points of these helices within sort of the errors of how well we could estimate them. And so that would be done with sort of a minimization of a least squared, like a least squared minimization. And that may depend on some parameters, which for instance says which of the particles you're trying to select to put into this least squared minimization. So our hope was to try to say, okay, well, this is a very valuable tool. Finding these vertices is a very valuable tool for classifying these different kinds of particles. It doesn't fit very well with sort of summarizing each of these trajectories with a momentum and a direction. So how can we sort of use this geometric information, the geometry of where all these particles go, inside of a machine learning tool? And one thing to notice is that this sort of thing we want to estimate, this position, this three-dimensional position of the vertex, although it is a minimization, we can actually define derivatives estimation of it is a optimization, and we can derive derivatives of these optimizations using the implicit function theorem. So specifically, if you know that at the minimum of once you've minimized this specific function, this least squared, for instance, with respect to the vertex position, that the derivative of that objective with respect to the vertex is equal to 0 there.
Michael, you
Yes.
have a question in chat that might be relevant now. If it takes too long, you can take it afterwards.
Oh.
So do you want to, it's regarding for multivariate optimization on the multiple parameters. Do you have a reference on how you achieve stochastic gradient descent over both parameters and multivariate objective and achieve good performance?
Right. Okay.
In a high dimension framework.
Right. So that's there. So let me go back. Okay. So there's a few different points there. A reference I think there's a nice reference called Automatic Differentiation for Machine Learning by Gunish Biden and others. That's a pretty good reference, I think. And there's a nice book by Barak Perlmutter, which is a nice overview of automatic differentiation. And everything about gradient descent basically, in many cases, relies on this automatic differentiation. And I think that's what you're asking about. So one point here that's sort of to sort of point out here is we can sort of compute derivatives in the forward and backward direction. So in one case, we'd wiggle the inputs and see how the output changes, sort of a sensitivity analysis. In the other case, we'd wiggle the output and see how the inputs change. And what actually happens is when you run this automatic differentiation in forward versus backward mode, you actually can very nicely either compute full columns or full rows of the Jacobian in sort of one pass through this graph. And what's very important with backpropagation is that if you have a sort of a scalar output function, so like in machine learning, you always have a loss function, which is typically a scalar valued, that you can compute the derivative of the loss function with respect to all the parameters, no matter how many there are, in sort of effectively one pass through the program. So you evaluate it once in the forward mode to get all the values here, and then you basically evaluate it again sort of backwards, accumulating the gradients one more time, and you'd get the gradient of the output with respect to all the inputs. So if you have a multivariate function on the output, you could do the opposite. You could use forward mode differentiation to get the derivative of all the outputs with respect to one input. So the question you asked seemed to be, if I have lots of inputs or lots of parameters and lots of outputs, how could I do that efficiently? And you sort of can't. you will end up having to compute the Jacobian row by row or column by column. And so you ideally, like in machine learning, the sort of key is that you can do this efficiently with this backwards mode autodiff. Did that answer your question?
Yeah, sort of. I think I can discuss a little bit offline or maybe at the end of the presentation. Thank you.
Yeah,
okay,
thanks.
Sure. Okay. Right. So, Anne, I don't see the questions come up. So if you can interrupt me, that would be great.
Sure. Thanks so much.
No, thank you. Right. So, so I think we were getting at this idea of implicit differentiation, where we can define the derivative at the minimum of this objective, and that gives us a way. Also, if we compute one more derivative of this function g, then we can actually define the derivative of the vertex with respect to any parameters coming in. And so what we've effectively done is sort of created a differentiable optimization. And this sort of comes up a lot if you've ever been working on sort of like bi-level optimization problems, where you use these tricks to sort of help solve the sort of bi-level optimization. And so we can sort of use that to integrate this sort of physics code, this idea of fitting vertices or finding where trajectories or curves cross, into a larger machine learning system. So we have sort of this weight predictor, which is a transformer, which will try to predict which of the particles we want to fit in this vertex. Then we've got this vertex, which is effectively optimization. That's basically a layer of a neural network that computes an optimization, the output of an optimization. And then we can feed that output of that optimization into downstream neural network components to solve a bunch of tasks. And so this is a nice combination of machine learning and physics code. And it does work. It's sort of here on the x-axis is sort of our signal true positive rate, our signal efficiency. And the y-axis is for some reason, and we like to compute 1 over the false positive rate. So higher is better here. And so the dashed lines are sort of without our physics code. And when we add in this physics code into this machine learning model, we jump from the dashed line up to the solid lines, which are something like 20 to 40% improvements, or roughly 20 to 40% reductions in false positive rates. And the red and blue here are just two different types of backgrounds we'd want to be able to reduce the false positive rate of. So in both of these cases, we can reduce the false positive rate by sort of 20 to 40%. Right, so adding physics helps. Adding this physics code and being able to optimize it all together, it enables us to better sort of optimize our physics data analysis tools. But I sort of just was discussing sort of taking derivatives of functions, but actually machine learning is sort of has stochasticity in it. So sort of machine learning is automatic differentiation is really great for differentiating deterministic functions like y equals f of x. That's really what automatic differentiation does. But in machine learning, we're really sort of computing a Monte Carlo expectation value, right? We're sort of sampling events like, and that's in this case, we're just getting some distribution, some samples of the distribution of cat faces. Then we're evaluating some loss function, and we want to take the derivative of that loss function with respect to the parameters. And when we sort of write that out as an integral, what's very important in here is that those sort of examples that we're sort of sampling, they don't really depend on the parameters of the neural network, right? We only have the parameters that we want to optimize in this function and this loss that we want to evaluate. So because there's no parameter dependence, even though this is an expectation value, it's a sort of stochastic estimation of the loss, averaged over many examples, we can pass the gradient right through that integral and compute the gradient of the loss function, and this form of this is now basically an expected value over the gradient of the loss, or whatever function we're evaluating. And so this is sort of the easiest case. Basically, we have an integral, we're gonna or an expectation value, and we can basically turn the gradient. When we pass the gradient through, we get an expected value of the gradients. And that's basically how most machine learning systems sort of do their optimization. Take the gradient of the neural network and update it. But sometimes the cases are a little bit harder. So here's an example of a variational autoencoder. And this system is a little harder because there's going to be stochasticity in the middle of the model. So we start by having some sample, for instance, of our cat faces. We're going to encode that into a probability distribution that basically then depends on the parameters of this neural network. And it's the probability of some latent space, some latent variables we don't know, but we're going to try to learn. And we're basically encoding this into a distribution that will then sample from that distribution and try to decode it. And in this way, we're sort of learning a posterior over these latent variables conditioned on the input. And if you look at the way you'd actually write down this loss function, it would basically be the expected log likelihood of the data given the latents, where the expectation is over this posterior. And there's also an expectation over it's basically the KL divergence between the posterior and a prior distribution. So I'm not going to talk about the details of the variational autoencoder's loss, but I want to focus on the point that this neural network is basically trying to predict some distribution, and so it depends on the parameters of this neural network. And effectively, your sampling from these expectations are taken with respect to a distribution that depends on the neural network parameters. So now this is a different case than we saw before, because we can't just simply pass gradients through and have an easy time dealing with computing these expectation values. But there is a trick. So most of the time, for instance, we'll think about, sort of encode, this neural network will encode parameters of a distribution that are, for instance, a Gaussian or a normal distribution. And so what we can do is actually think about, well, what we're really doing is taking this encoder and predicting the mean and the variance of a normal distribution. And then in order to sample it, all we have to do is sample some noise variable that's sampled, for instance, from a normal distribution with mean 0 and variance 1, and combine this information with the mean and the sigma to get a sample of z, to get a sample from this sort of posterior distribution. And now, since this sort of stochastic part of the system doesn't depend on any of the parameters, our gradients can sort of pass through, and we can train this whole system sort of end to end or all together. And that's basically, we've pushed the parameter dependence from the distribution we're taking the expectation value with respect to into a sort of the variable that we're sampling. This z is now a function of these parameters, sort of mu and sigma. And this is an example of what's called the reparameterization trick. And this is how we basically deal with stochasticity or stochastic nodes or stochastic computations inside of neural networks, as long as that's all a continuous system. So instead of sampling directly from this distribution, we'll rewrite the variable, sort of the random variable of interest, x, as some function of some noise and some parameters, and we'll have a very simple noise distribution. So we saw this Gaussian example. If we want to sample from a normal with mu of 0 and mu and sigma, then we basically sample noise from normal with 0, 1, multiply by the variance, or the sigma, and add the mean. And so you can see what basically happens to our gradient estimator of this expected value is we push the parameter dependence into the function, and now it's into the objective. And now we basically have a composition of functions and a distribution that doesn't depend on our parameters. And we can again pass the derivatives into the system and just use the chain rule to get our gradients. And this is how a lot of the sort of variational methods in machine learning are how you deal with the stochastic part of those variational methods. Okay, so I've given you another sort of one of the tricks for computing gradients now of machine learning systems that have stochasticity in them. And so you might ask, is that all we need? Are we sort of done? And of course, the answer is no. We didn't talk at all about discrete processes. So discrete random variables actually come up all the time in high energy physics, and it's one of the major challenges that makes it impossible to make our sort of physics code fully differentiable. So we have all sorts of sort of branching and showering processes. Here's an example of a particle streaming through and interacting with detector material here in gray, and then splitting into pieces. And each time it interacts, there's some sort of discrete random variable that decides, are you gonna split into more particles or not? And so it's a sort of discrete branching process. And we also have clustering algorithms all over the place where we have different energy depositions that we need to cluster together, or different particles we want to cluster together into jets. And these clustering algorithms also require discrete decisions. And so we need something else to deal with derivatives of programs that have discrete random variables in them. So one thing I want to point out is sort of what happens when we look at programs with discrete randomness. So here's an example of a program. We're going to have this function f of x. It's x squared plus a Bernoulli, where the Bernoulli's the probability of sampling the Bernoulli of being 1, we call it theta here. It depends on some function of x, in this case sine squared of 2x. And you can see here on the bottom, this is the sort of short code on the left, but you can see here what the samples from this program look like. In green are the different samples, and if you look at the sort of average of this program, it's sort of this nice smooth and red function. And you can sort of work out what the expected value of this function is, and indeed it's some simple sort of smooth function of x squared plus sine squared of 2x. And you can see from looking at this expectation value that we can very directly then compute gradients of that expectation value with respect to x. So even though there's sort of this discrete behavior here, and if we were to sample a discrete number and say, if I wiggled a parameter and I just look at a Bernoulli, how does a sort of discrete number change continuously? You can't really define that so easily. The expected value of this program with a sort of discrete random number in it is nice and smooth and has a well-defined derivative. And so we want to be able to use this fact to deal with derivatives in our programs, derivatives of discrete random variables in our programs. Now, if you just tried to take this exact function and give it to one of these automatic differentiation systems like PyTorch or TensorFlow, the derivative you get out would basically be that it ignores any dependence of this variable x coming from the Bernoulli, and it'll just basically take the derivative of x squared and give you this blue line. That would be the derivative as a function of this value x. That's the derivative that automatic differentiation would give you, when the true derivative should be this sort of wiggling sine wave. And so standard A2 automatic differentiation tools don't know how to handle this sort of discrete randomness, and we need another approach. And there's actually many different kinds of approaches, and this is sort of a hot topic in different corners of the sort of differentiable programming space. So we'll talk about sort of these two on the left a little bit, what are called score functions and stochastic AD. And for those of you that may be familiar with it, the system stochastic AD that we'll talk about a little bit in detail is related to what was known, it was also often called smooth perturbation analysis, which there was a bunch of work, I think, in the 90s. You can also not try to actually compute derivatives in some, so these methods take a fair amount of work. You could also just approximate derivatives using like smoothing or relaxation techniques. So for instance, here's an example where if you want to sort of rank or sort a bunch of discrete numbers that, for instance, live on, in this case, a cube, you can try to optimize in the volume of the cube, just try and rather than just trying to figure out which of the corners of this cube is the optimum for some problem. You can build surrogates, so basically approximating the complicated non-differentiable or discrete behaviors, approximate it with a neural network and use the neural network to give you a derivative, although you don't know if that'll give you a reasonable derivative. There's finite different methods and even gradient-free methods like Bayesian optimization. So we'll basically just talk about a little bit about these left two methods. So the first method is called score functions or reinforce, and we'll see why it's called reinforce or sort of. You might not be surprised to find out that this is very useful for reinforcement learning. So in this case, we're sort of trying to compute this derivative of an expectation value of a function, where the distribution that we're taking the expectation value with respect to depends on the parameters. And if I sort of just were to write out this integral and push the derivative inside, you'd see that this you basically have the derivative of this distribution times some function, and that's no longer looks like an expectation value. It's not something we can sort of turn into a Monte Carlo expectation. But an important sort of identity or calculus identity is the derivative of the logarithm of p is 1 over p times grad p. So multiplying this 1 over p to the other side, we see that we can turn what was the gradient of p into p times the grad log p. Okay, so now this suddenly looks like we have some distribution, and we would want to take the expected value of the function of interest times the gradient of the log probability distribution. And that is exactly this, when looked at as an expectation value, that's exactly what's called reinforce, or basically the function times what's called the score function, as you might have seen or also comes up in things like the Fisher information. And so in this case, we have now a way to sample, for instance, you take samples of examples and compute an estimator of the gradient of this, for instance, if f was a loss function, compute the gradient of the loss. And so this is very nice because we only have to compute the gradient of the density. We don't need to, for instance, find a way to pass gradients or compute the gradient of x with respect to these parameters. If it's discrete, that may not even make sense. And interestingly, f doesn't necessarily even have to be differentiable. We just need to be able to keep track of these probability densities and compute this f times grad log p. And that's exactly what happens when you're doing reinforcement learning. You might, for instance, if you're training a system or to play a game that can move up, down, left, or right, these sort of discrete actions, you take a trace or a history of all these actions and keep track of all the probabilities of those actions and use them to compute this gradient estimate. So that's sort of reinforced, and it's sort of the main way that reinforcement learning algorithms are optimized at this point in time.
Michael, quick reminder,
Yes.
you have about 10 minutes left.
Oh, I think I lost a lot of time with my going
that's
offline.
Okay. Oh, that's okay. You should have a discussion afterwards if you can stay around for a few.
Yeah, no, that absolutely. So we'll sort of have a quick look at some new ideas that have come about called stochastic automatic differentiation. Basically find a way to be able to, even if you were to have sort of stochastic randomness in your computation chain, in your computational graph, to be able to integrate gradients of those discrete random samplings in a sort of automatic differentiation kind of way. In other words, there's a sort of composition rule that allows you to combine a bunch of different computations that have involved discrete random variables and accumulate that to form a derivative. And the way that derivative estimator looks is you have the sort of standard AD component, any gradient of f you need to take, and this other part where you get a weight, and we'll talk a little about what this weight is, times the difference between the sort of random value of your function and some alternative value, sort of an alternative random value that you might have gotten. And so I'll try to sort of take you through the way that this works, although we don't have much time. So the one way you can sort of think about discrete random variables is actually sort of as continuous ones. And so if you imagine a Bernoulli random variable, you could imagine sampling a uniform random number, and the uniform random number would be 0 if this uniform omega was between 0 and 1 minus p, where p is the Bernoulli parameter, and it would be 1 otherwise. And so if you were to sort of write down the expectation value of the Bernoulli, it would sort of have this indicator function of omega being greater than 1 minus p. Now, what you sort of see is what you basically have is a computation of this integral where you have a parameter dependence in your boundaries. And this makes it basically impossible to compute, for instance, Monte Carlo expectations. You'll never sample the boundary, and you'll never be able to compute a gradient if you just sample uniformly between 1 minus p and 1. You'll never be sensitive to this parameter. And in fact, if you try to give this program to AD, it'll basically tell you the derivative is 0. But of course, we know from the Leibniz rule of calculus that there should be no problem computing gradients when you have parameter dependence in the boundaries. And so that's basically what you need to account for if you're thinking about discrete random variables as sort of uniform random variables with boundaries that depend on these parameters. You can derive gradients that way. And so you can sort of think about if we had this program, and if what we're basically trying to do is if we were to wiggle this Bernoulli parameter p, it's like moving this boundary. And as we move that boundary a little bit, we end up having some small region where if we would if we had moved this parameter, the program would have flipped from 0 to 1, and there's some small probability for that to happen. And if we, so basically this parameter beta is accounting for the derivative of the probability of this small program change. Basically the derivative of the probability of there being a jump in the program as the sort of, the change in the parameter goes to 0. So basically, as we make an infinitesimally small change to the parameters, there's some gradient of the probability that this program would jump. And the difference between these random variables is telling you exactly how that program would jump if that happens. Just for posterity, if you want to know exactly what this beta looks like, it ends up looking like the derivative of the CDF divided by the PDF, but we don't really need to get into the details there. What's important is that we can compute this at every step of a program that has discrete randomness. We can combine all these weights to give us a full derivative of the program. And so the way that this sort of looks is we run our program in black. That's our primal program, the main program. And at every point, these black dots where there's a discrete random sampling, we could branch off another program that would be basically an alternative version of that program. And from that alternative, we could compute that gradient we saw before. And you can actually, ultimately what you do sort of for efficiency is you only select one of these alternative programs to give you your alternative your alternative y in this equation. So we run our program, we sample an alternative version of the program, run it to the completion, and then we compute the difference and the weight, the sort of weight, which is the sort of derivative of this program having flipped at each of these points. So this turns out to give you a very correlated path. The program that you sample will be very similar to your original program, keeping your variance low and trying to compete with one of the big problems of score functions, which is they tend to have very, very high variance. Okay, so I really like this paper, and it's from some of our colleagues at MIT. So I wanted to explain it to you a little bit because we sort of did try to dive in and start to address some of those challenges of taking derivatives of discrete programs. And so specifically, how would we take a derivative of a program that has this sort of branching process in it? As a particle flies through, it branches. Every time it interacts with the detector, it may or may not branch. Some discrete probability for that happening. And if we wanted to optimize, for instance, where these particles stop, where they lose all their energy, we need to be able to take the derivative of this program that has this branching process in it. And so we wrote a sort of toy particle branching or particle showering process. And we're going to try to optimize this detector, the radius of this detector, so that the particles, the average interaction point, where they interact, each point they lose energy, and the average sort of interaction happens at some specific value. I think we'll choose 2. And so we're going to vary the shape of the detector and try to optimize it. And we implemented this sort of idea of alternative showers, so we can branch off and run different showers or different branching processes at each point of the program. So here's a video showing that we can do this. On the left is the program. We sort of run one shower or one branching program at a time. And the detector sort of changes shape to sort of make sure that these showers stop at an average radius of 2. And you can see the loss function, since we only have one parameter, the loss function is easy to sort of visualize. And each of these sort of samples and are shown in red, and the yellow line shows the gradient as we sort of optimize this system. So indeed, we sort of written the first sort of optimization right through a branching process, and sort of one of the first, as far as I know, the first sort of differentiable branching program. So ultimately, what we really care about is how the variance of these estimators compare. So on the left, as a function of the sort of radius of the detector, you have a bunch of different methods, but what's sort of important is in this sort of dark red and yellow are the variance comparisons between this sort of stochastic AD, this alternative where we had these sort of alternative showers, and the score functions here in red. And they have very similar variances, so we haven't been able to sort of beat some of the sort of modern techniques and score functions, but it's very similar in variance. And you can see on the right or in the middle, sort of these are the box plots comparing at a specific parameter value, the sort of 50% confidence intervals for sort of the stochastic AD method and the score functions here. Sort of in yellow is a score function with some tricks to reduce the variance, specifically using control variance. On the right, you can see sort of the optimization as a function of the number of the steps, and as compared to sort of numerical methods or these methods using the score function or the stochastic automatic differentiation optimize much faster. Okay, so I think I sort of rushed through the end, but I think that sort of brings us to the conclusion. There's a lot of really unique opportunities at the LHC and future colliders, and if we can make the most out of the data, we may have the possibility of discovering completely new particles and forces. And so differentiable programming gives us a powerful method to do these sort of optimizations, provided that we can figure out how to compute gradients of the different parts of the programs that show up. And when we can do that, it enables us to sort of embed physics knowledge directly into our machine learning tools to build more powerful systems. So as I mentioned, not everything is easily differentiable. There's lots of challenges along the way, especially for these discrete programs, but or programs with discrete randomness, but we're making a lot of progress on developing the tools to be able to provide those derivatives and those optimizations. So that sort of brings me to the end of the talk. Sorry, I had to rush a bit, but thank you very much.
Yeah, thanks so much.